So, dear student, let us go to the last chapter of our work, energy, and power. And about this, we are going to be talking on power, which we are going to do in one slide. Because power, I believe everybody has power. Now, as we have all discussed before, we can define power, which is the first thing we need to keep in mind for this particular slide. We say power is defined as the rate of doing work. So we can write that power is the rate of doing work, which is most likely what every one of us might have come across in most of our what textbooks and test materials. We can also define power as the rate at which energy is expended. Now, when we say rate, I know you might have also known that whenever you talk about it, we are talking about time function of that thing. So from our definition, the rate at which work is being carried out is called the power. So we can give an illustration to that. It's quite simple to understand before we write power numerically. That is, if you have a boy that is actually standing on top of a stairs, which you can just picture, just a quick one for understanding's sake. There's a boy on top of a stair, which is trying to climb up a stair. And what he's trying to do is what we said, the boy is trying to climb these stairs. And at a time t is equals to, let's take for instance 1 second, he was able to climb the stairs from that towards this particular point. Now, because he is covering a distance, and by doing that, we talk about force energy. Now, force was applied to climb from one stairs to another. So we can actually say the power expended by this boy, power can be expressed numerically as what the fact as a work done and moving from what the downward part of the stair to the upper part of the stairs. So we said that the time function, that is the work done, divided by the time. So this is the way we relate time, we relate power with respect to what time and work done. So basically, I know you might have learned about all these in early classes, and we are only trying to show some illustration for you to understand that power is a function of time. Again, if the same boy is now what, or another boy this time around, is now climbing the same stairs and is now using, let's say the power used by this guy was P1. And in this case now, this is using time of 2 seconds to climb the stair, and they say the power is P2. In this case, since T1 is less than T2, from illustration, we can say power used by this that's actually used by 1 second is higher than the person that used 2 seconds. I hope you understand that illustration. Another way you can look at it from your own knowledge of formula to actually understand concept is that power is inversely proportional to time. So the rate at which work is done, how quickly work is done, is the measure of the power. Do you understand? So if work is done at a lower time, that means you are saying that person is having more power. And if work is done at higher time, the person is having less power. Here we can say P1 is greater than P2 because in this is the illustration, because the time factor taken in 1 is less than the time that is taken in 2. I hope you understand the concept. And this is the way we relate power in physics. Another thing we can talk about the introduction and type before we go to types is we can also talk about the SI unit, which is actually showing behind me, which you guys can see. We say power is measured in what? We say work done is measured in joules, already discussed, and time is measured in seconds. So directly we can say the SI unit of power is given as joules per second. But majorly in our test materials, we have different SI units for power. Students should understand that. Now, most power in our physics textbooks and material are in watt. So I want you guys to understand that 1 watt is the same thing as joules per second. So either you use watts or you use joules per second, you're actually saying the same thing. So let it be known for all students that when we are doing the illustration of power, power is measured in watt or joules per second. So the SI unit of power is watt, which is more or less like the name of the person that discovered bulb, which you might have come across before. So now, don't make mistake by thinking joules per second is different from watt. They are the same thing. Another dimension of power we can also talk about is what we call the horsepower. Now, and it is not the SI unit, please note. But if power is related in horsepower, you can keep them in note. Power in horsepower, that is what we call HP, will be needed to be converted to watt. So by calculation and approximation, we say that's 3 over 4, okay? So we say 1 horsepower is the same thing as 746 watts approximately. So students can also keep this at the back of your mind because it's kind of very, very important to know this conversion. In some cases whereby you are doing numerical and the SI unit is not in joule per second, joules per second, or in but was rather given in watt. So be careful about these, and that is that. Another way you can express the formula of power, which I also think I need to talk about under this slide, is that power, we said, is work done by time, which we have shown there. And we have also discussed or talked about the formula for work done. We said is the product of force multiplied by the what displacement or distance, as the case may be, divided by time. Now, everybody knows that when we talk about distance or displacement over time, that is velocity vector. So velocity is displacement by time and speed is distance by time, which you have learned also in early classes. So we can also say the power formula can be in terms of force multiplied by velocity. So anyhow you have it, both formulas are very good to actually keep in mind for numerical purpose. And that is what will lead us to type of power. Because now I have given you an illustration for the first formula of power as work done over time. I'm also the same person that gave you another illustration as power equals to force times velocity. So the next thing we're going to talk about as we move into the next slide, in continuation to introduction to power, we are going to talk about the types of power. About types of power, let us keep that in mind. Types of power. In physics, we classify power into two. The first type of power is called average power. When we say average power in physics, and the second type, before we go into one of each of them, is called instantaneous power. Instantaneous power. So these are the two types of power according to the classification in physics. Now, when we say average power, what we are trying to talk about in average power is that we are talking about what the sum total, when we say average, sum total of all the work done divided by time. So we can say it is given as change in work done divided by change in time. So always keep it at the back of your mind as the average power is defined as the rate of change of work done with respect to time, which is simple to define. So be careful about the formula. Whenever you use the formula of work done divided by time, the type of power you are calculating is what the average power. And the second type of power, which is also very, very important, is the instantaneous power. And about instantaneous power, we can also keep that in notes because we've been talking about instantaneous. That is, we are classifying power at an instant of time. And when we classify anything at an instant of time, you already know, if you have been following our classes, that we are going to do a little bit of differentiation. Now, from that, if you want to calculate instantaneous power, keep it at the back of your mind. You are saying the formula for instantaneous power is average power. Most time you see average power is written as a power. I think that is also important when you see something like this, because of some of us that we are attempting A-level questions, that means average power. So when we say instantaneous power, which I give by formula here, don't worry, I know you are following. Rate of change of work done with respect to time. Now, here, instantaneous power is talking about power at an instance of time. So what we are talking about here is that instantaneous power, power instantaneous, numerically, is given as We have a force vector multiplied by, you can see velocity vector is what? Distance over time. So whenever you are considering this type of power, this type of formula, when distance is changing with time, such power is called instantaneous power. So what we are trying to say here is now, we know that rate of change of distance with time is called what? Change in velocity vector, which is what? Displacement divided by time. So by and large, what I'm saying, my dear student, is that students should keep it at the back of their mind that when you are using formula of for instantaneous power, what you are expected to use is the word change of the force multiplied by the velocity vector. So the two formula we have talked about at the beginning of the introduction are very, very valid. One is valid for average power, while the other is valid for instantaneous power. So keep this at the back of your mind. We are going to go to illustration, and also you can also take down a note, which I think is also very important. Power is not something that is too much for us to watch. We are not going to be talking too much on power because basically power is not that it's easy to get. If you want power, you can easily get power. Can you guys hear me? I said you can easily get power if you want power. So anyhow, we can now say take a note that what power can be negative or positive. Can be negative or positive. That's another important note. You remember when we talked about work done, we said work done also can be what? Positive or negative. I said when work is done by a body, that is when energy is being supplied. When energy is supplied, that is what? You are giving out what? That is a negative power. But when you are gaining energy, what I mean by that is supply of energy is negative, gain of energy is what? Positive in terms of work. The same thing is applicable for power. Now, as you also can also say work done with from our work energy theorem, which we have discussed. Remember, we talked very well about what work done can be converted into what? Energy. So if you say some people with average power is equals to energy divided by time, not a problem. What you are saying is, well, maybe there is a conversion of form of energy. Work done has been what? Converted to energy because distance has been covered. And for work to be done, you need a force. And for you to give in a force, there must be an energy. This is the way we relate all these stuff. So now, I say power can be positive or negative. So when we say power is positive, we mean it is what? Let's start with a negative just to keep down a note. The negative power means we said negative power means negative means supply of energy per seconds per seconds. Positive power means what's that, guys? Gain. Very good. Gain of energy. Gain of energy per seconds. So, or it also depends on the way the examiner actually put it in numericals. It is not necessary for it to be in seconds. It can be in minutes, it can be in hours, it can be in any form. So the gain of energy and the supply of energy bring about positive power and negative power. So this is all about power, my dear students. What we are going to talk about now should be calculation of powers and the illustrations at the end of the video. I do tell you it is not sufficient for preparation of A-level physics until you actually practice on your own, or still you can still get our practice section on all the areas of all the concepts we have discussed. This is just for us to do one or two things. And as usual, I do tell you it is not prepared by me, it's always prepared by one of our students. You understand? My students generally, they do it in section. So let's go to the illustration side and see what we have. Fine. Good. About the illustrations side, we are told here that starting from rest, we don't know what is starting from rest, maybe a car or anything. Okay, it's a car. A car of, don't mind me, I want to condemn him again. A car of mass 1,000 kilogram accelerates steadily to 20, acceleration should be 20 meters per second square. I will see something to correct in 10 seconds. The average power developed in this period is we have discussed average power from our understanding is our work done divided by time. I hope students are still here. I hope you can hear me. work done divided by time. So if we say work done in terms of energy, work done is force times distance, or you say energy divided by time, anyhow you want to do it. The time is given by 10 seconds, then the mass is what you can see. It is from rest. So we can say work done has been converted to energy because it has gained some energy divided by the time. So you don't have issues. That's why I'm writing everything out for us. So directly, my dear student, we can calculate the work done. If you want to do it in your own way, you can say work done is force times distance, already discussed, which is important. And if you want to do it in terms of because it has been converted to energy, and what kind of energy if something is at rest before and it started moving, that is kinetic energy. So motion, you have a half mv squared, which I believe you all might have studied in your early classes, mv squared. So now here in this context, we are only giving mass. Instead of that, we are giving what the acceleration. So if it is acceleration, then we have to convert acceleration to velocity. We know velocity is equals to, is starting from rest, directly I told you, under root of 2as. I hope students still remember this. So here, what we need to understand here is that in this thing, we only have, the distance was not given. So I'm thinking there's an error here, but notwithstanding, let's see. Don't let us condemn until we finish. So it is starting from rest. It can move and accelerate. So if we say v squared equals to under root 2as, we know we need velocity. Do we know acceleration? Yes, we do. Do we know the distance covered? No, we don't. So it doesn't stop us from trying another formula. If we need that, we can say the distance is not given. So we can use this. We can try v is equals to 80. This is very correct. You can see this now. So if we say v equals to u plus 80, I'm not using u because it's starting from rest. What is the acceleration? 20. What is the time? The time is 10. What is 20 times 10? 200. I hope you understand this. And that is that. So directly we can now come to the formula. Energy is half mv squared. Everybody knows half times the mass is 1000. The velocity is 200 times 200. I hope you are still here. So this gets cancelled out. You can say this is 100. 100 times 1000. This is, you can say, this is 2. Then put the total number of zeros. So you can just write it as 2, 1, 2, 3, 4, 5, 6, 7. 7 zeros. 1, 2, 3, 4, 5, 6, 7. You are dividing the answer by the time, which is 10. You can do it in another way. That is one thing about physics. Then this gets cancelled out. How many zeros do you have? You have 6, 1, 2, 3, 4, 5, 6. You can say 2 times 10 raised to the power 6. And the answer is in, you can put it in watts. And if you like, you can put it in joules per seconds. I hope you understand this. And that is one thing about understanding concepts. You will not be afraid of solving questions. That is that. No, you will be able to read the mind of the examiner. The next one is also asking us that the average power required to lift a 50 kg of load to a height of 25 meters in, this is not correct. I don't understand what is here. 25 meters in 2.5. Is it 2.5 seconds? Because there must be a time. This cannot be meter. This cannot be meter. So one should be seconds. So this should be, can have 2.5 meters. So there's an error here. But all the same, average power formula is always equals to, we need to know, you can't have two values in meter. So one should be in second. I guess it should be in seconds. I'll leave it for you to do. So average power is work done divided by time, which is the same thing as what we have just solved there. We are dividing it by time. So directly is what you can do, guys. So work done has been converted to energy because 50 kg of load is moved to an height. So the same thing as what we just finished doing now. But now we are talking about free fall motion. You understand what I mean by that? So if you need to get the velocity, if you want to go by velocity, because it's being raised, it's half mv squared, just like what I have solved. So now it's motion under gravity. We should know that v squared directly is equals to 2gh. You understand? Instead of 2as now, it is 2gh because the body is going under gravity. I hope you understand this, and I hope you can do it. So you can just say v squared is 2 times 10. G is always 10 or 9.8. That is 20. The height that was given us is 25. I hope students are there. 20 times 25 should give us 500 if there's no mistake. And I think that is right. So V square is 500. And I told you in one other video like that we did that why I'm using V square is because the formula I want to use here is having V square. So I'll just plug it in directly and get my answer. So the work done here in form of energy is half times the mass was 50. The V square is 500. What do I know, guys? This can go here in 25. So I need 25 times 500 is what I need. 500 times 20 is 10,000. 500 times 5 is 25. That's 12,500 if I am not mistaken. So this is 12,500 joules of energy or work done that has been converted to energy. Anyhow you want to say that. So you are dividing 12,500 divided by the time. I'm working with that to be time. And I told you, I don't prepare this slide. It's always prepared by the student for me to solve. So there we have 12,500 divided by 2.5. You can go by cutting with your calculator. I have one here. Let me pick. And directly, this should be 5,000. We don't need to waste our time. So, and this is giving us 5,000. You can confirm that. And you can write watts. And if you write, you can write joules per second. So anyhow you want to write it, because I've written right here, I just decided to use joules per second in that. So I think we still have one more slide here, which is the third question and the fourth illustration. Oh, wow. The question here is, oh, no question. I think I need to get what is here. We have to find the average power from point O. Wow, wow. This is a nice one. From point O, which is here, to point A. We are looking for average power. Yes, not a problem. We have studied average power as work done divided by time. I hope students still remember work done divided by time. Remember, work done is we have force times distance, which we've also studied. So now what I need here is just two things. I can say this is work done is force times distance. In this direction of motion, I need to be very, very careful, because what I'm talking about here is motion under gravity, because the body is moving with an initial velocity of u meters per second. And I think it is not having an angle, though we can show an angle which is always towards the horizontal. It's not a problem. Then again, what we just need to understand here is just to calculate direction of our force, and it's moving towards what you can see. It is a parabolic motion. That is a little bit of projectile knowledge is needed here, and moving along towards the time t here, which we might have studied also in our LA classes. So what I think I need to do here is just to get the value of the force and to get the value of the distance. Now, here, if I say power is equals to force times velocity, that is the formula we use for instantaneous power. But the question asks the average power. So what I will just do now is to get this. Now, force is the same thing as weight. I hope students know that, because we are talking about body that is going what in parabolic motion, which you call projectile motion. You can see the motion of the part are going to have some trajectory, which you can also calculate the equation of the trajectory. You have all those videos available. Projectile motion, which is an example of 2D motion, 2 dimensions. So directly, force here is mg, and distance here is what is recorded by height, Abi, which is h. So this is my work done, mgh. Then my time, the time for this body to move from here to the point of A, if everybody understands projectile motion, the time taken is always u sine theta divided by g. So directly for this solution to this answer, I can now write, I hope students are getting this, work done, I said work done, average power. Average power is equals to the work done. What is the work done, my dear student? mgh. We are dividing the value by, or better still, because this will be retarded by gravity. So I will say negative mgh because of technical question, divided by the time. What is the time, my dear student? U sine theta divided by g. So if you go by that, final answer to the question should be g gets cancelled out. But let me show you, because you always want me to show you the illustration. So be negative mgh. We are dividing the answer by this. So if I turn this 2 times, this will come out. U will not cancel out. You can see. Then you have U sine theta. So what happened here? You have m negative mg square h over U sine theta. So this is the answer for the average power, and that is very correct. So please keep it at the back of your mind that you just can have some technical question like this, which you are asked to calculate average power, especially for those doing advanced illustration and advanced JUPEB and all the other forms of advanced examination. And the last but not the least, for this work energy and power, which is the end of work energy and power for now, we can look into this. The question, I think, is the same thing, but the only thing is moving from the point of this, which is the initial point, along the time t. This time around, we are to calculate instantaneous power. For instantaneous power, we have talked about that. We said when power is instantaneous, P instantaneous, the formula we use, IST, anyhow you want to write it, is always equals to, I believe you are following, force times velocity. Now, it is very easy to understand the direction of the force. The force is moving with respect to, you just need to be careful. The force is negative mg. I hope students understand why it is negative mg, because it is a projectile motion, which is just like this, which is retarded by what? Because the body is going up, it is what? It is going against gravity, the way we talk in what? In junior classes. So now, guys, this is the force, but the velocity are happening in two components. I hope students are here. Velocity is going to happen in two components. The first component is the velocity along the x-axis. Now remember, if this thing is having an angle of theta, let me quickly show you what we have talked about in that projectile. If you try to bring about motion in 2D, you resolve this angle into what? Into two planes. It is moving with u meters per second, according to the student that set this question for me. My student are the one testing me now. So now here, if this is moving with u meters per second, as you can see, resolve this u into a component. This is opposite over hypotenuse. So vertical is u sine theta, which is always retarded by g. And horizontal is what? You can see u cos theta, which is not retarded by any form of gravity. I hope you students understand. So the velocity are in two components, which you have to understand. So the components of the two velocity are, remember, in motion. You talk about velocity components are, if you talk about the resultant velocity is always a square root of the velocity of x plus square plus that of y squared. Do you understand what I'm trying to say? Because we have two components of velocity, which we have to what? Which we have to put down in our velocity. So, and that is why I am going to, the way I'm going to solve this question. So it might look a little bit tough because I think it's an advanced illustration and we needed it. Now, directly, what you need to do from here is just, I've resolved the velocity along the x-axis now. It is not what? It is moving and it is not being retarded by any form of what? Any form of what? Any form of gravity. But along this, we have gravity. You understand? If you want to go by that, if you want to actually go by that, you can say the velocity along that side is equals to, do you remember the formula or speed equation formula? S equals to, was I can actually need that. S equals to, in fact, ut retarded minus half gt squared, because I'm using this, I need the distance. So ut along this place, you can say S equals to, if I'm solving the distance along the horizontal, you can say it will be u cos theta, that is u cos theta t, u cos theta multiplied by t minus half gt squared. Why am I doing that? Because this thing is moving towards a distance. I can't just say the body is having this of negative mg. So negative mg is only for what? For one direction. So I have to calculate the distance along this direction. It's very important. So what I will do now to finish this because of time is just for us to understand that we need to get the what component of velocity vector. Now what I will do now is that I told you along the x-axis, it is given as you can see this is x-axis, u cos theta. So along the y-axis, it is given as you can see, it is retarded by the gravity. So if you want to go by velocity formula, you have also have studied to be u minus gt. I hope students understand this. So now along that, it is given as a u, there is a u sine theta minus gt. So this is the velocity at s component. I hope you are getting it. And the velocity at y component is u cos theta. So at y component is not retarded by any form of g. So you said it is what? U cos theta. So you can see it is a lot of clumsy something. So here we are going to get the resultant velocity, which we are going to substitute here, which is what? The addition of u cos theta and whatever u sin theta then minus gt. So that is what we need to understand. Another thing is we need to introduce vector, because if we did not solve it by vector, it will be wrong. Along this component, you can see this is u cos theta. What is this cap? We call it I cap. I hope you know. And along this component, it is what? U sin theta, and that is what? J cap. Y is J, this is I. So like I said, I will leave this for you guys to finish up because it's very, very long and the space I'm having here might not be enough. But I will take you through how to get the answer without having any issue. So the point is, this is Vx, this is V1. So if I don't want to put the direction, no problem, but it's because I want to do vector analysis. That is why I need to put I cap or J cap. Now here, why I'm doing that is because if two I cap multiply with each other, I times I, you know the meaning, you know what will be the answer when we talk about what our multiplication. So it is not going to be I square. You know, we said I times I is going to give you, you know what I mean by that. So please, and if you have issues, watch vector video. If you have issues understanding what I mean, what I'm trying to say is that you can multiply I times I. You can multiply what? If you have we have dot product and we have what? Cross product, which we call scalar and vector product. So in particular, if somebody asks me to multiply, look at this now, illustration 3i plus 2j multiplied by 3i plus 2j. Now, I can multiply I times I. Well, I times j will give me 0. So now, what I'm trying to say now is that the first component here is I cap. You can see the illustration is very important. Then here is what? Is J cap. When I multiply J, what I say is going to give you 0 for scalar product. So that is why only at this point, the only thing that will move in here will be negative LGT. You can see clumsy, but let me break it down. Now, the formula you want to use directly for those that want the answer, this is the way you do it. Power instantaneous is force times what? Velocity. So force along the direction of force is not just at one side. Formula for force, you know that formula for force generally is what? Mass multiplied by what? By gravity. Because the body is going with respect to gravity. And the velocity we are talking about, it is in two components. And that is why I'm trying to do this. You understand that now? So if the force is this, we are multiplying the answer. You know why I'm putting negative? Because it is going against gravity. And velocity is now the addition of this one square plus this one square. So you expand that and go over the square root. You get the answer. You multiply it by this. This is the answer to the question for instantaneous power. So I'll leave it for you guys to do. But what I just want you to do now is P instantaneous will be equals to negative mg times, now you have a square root of, I hope students can do this, square root of this, we have this is a Vs square is u sine theta, whatever, u sine theta minus gt squared, you put it there. It looks clumsy, but it's your work to do. Minus gt all squared. There should be a minus here, all squared. And see, look clumsy, everything is inside square root. M plus the y is what? U cos theta all squared. So that is your answer. And you can also substitute c to be equals to u sine theta over g. You can see you have a lot of work to do. So you finish this expression for me, and you get the answer for instantaneous power. So guys, excuse me, see you soon in my next video. I'll be waiting for the answer for this. I want you to do what? Break it down and let me see who's going to have it. So bye for now, and let's meet in our next topic.